hear a little bit more about photonic quantum computing. And as Mark mentioned, I co-founded a bit more than a year ago a photonic quantum computing company called Orca Computing. I'm currently an advisor for the company, and although I have a PhD in string theory, I'm more of a commercial or business person. So, I've tried to keep the technical part to very basics and maybe just use it as an introduction then to talk a little bit more about the commercial outlook for these technologies. So, I think everyone at Orca is always very happy to talk more about our technology and particularly our CTO, Josh Noon, and all the team behind him. So, if you have further questions or if there's anything that I can't answer here today, then I'll be more than happy to connect with them. So maybe, since I mentioned I do have a PhD in string theory from Cambridge University from a long time ago, but very soon after graduating, I sort of moved to we could call it the dark side, the commercial side. I did an MBA and spent most of my career working in finance and then working my way back into science from the startup point of view. So I was part of the C-level or founding team of several startups, and more so I got involved in science. And for me, and I think for everyone here today, quantum is one of the most exciting technologies of the past few decades. And the opportunity that we saw when we created our Orca, not only, it had to do with photonics, but it also had to do with the computing side of photonics. And I'll talk a little bit more about that. So, it's hard to put a number on the market size of quantum computing, but we know it'll be much larger than it is today. Some say it'll be 1 trillion by 2030. That I think feels about low, but it really depends on all of us working to make it happen. And what's been exciting over the past few years, even from when we started Orca to now, is that there's been a shift in how people talk about quantum. And before it was a little bit more of a, well, if we get a quantum computer, right? Then in the past several months, it's become, and I think it was apparent for all of us working in the field, but I think for maybe the general public, it's become apparent that it's not an if, but rather a when, and that's very exciting, right? I mean, we're certainly moving, maybe slower than one would hope, but we're moving in the right direction. And so there's a ton of different problems that quantum computing can solve, and I won't get into detail on those, but the interesting feature is that
Cristina, can I just interrupt for a second? All we see is a black screen. Is that intended or
no? You should see my my trillion market slide.
Unfortunately, we only see black screen.
Hold on
maybe
1 second. Let me Are you seeing?
Yeah, now we see a slide.
Now you see it, but when I go into presentation mode, you don't. I wonder if it's worth just me sort of making this smaller and smaller, like this.
I think that works. Yeah, that's great.
Sorry about that.
That's okay.
Yeah. So okay, so that makes more sense now. Thanks for that, Mark. So as I mentioned, there's a lot of, I think you all know this, but just as a matter of introduction, I think the opportunity is large and it cuts across many different industries. However, we still have what we call at Orca. Sorry, I'm trying to navigate this maybe like that. I think I need to. Sorry, I need to pull the small images on the side to be able to navigate the screen. Just bear with me 1 second. Sorry about that. I lost it. Sorry, I'm trying to recover the thumb. Oh, like this. Yeah, there. Okay, sorry. So that's the only way I think I can navigate this. I hope that's okay. You know, the opportunity is large, but at Orca we talk often about the quantum gap. And let me explain what I mean by that. So basically, over the past few years, we've seen a proliferation of companies focusing on quantum software, quantum algorithms. And I think this has been driven mostly by quite a lot of interest. I wouldn't call it demand just yet, but interest from the end users at the very top. So certain large corporations that understand that quantum is the future have been, you know, just trying to engage these companies. However, there are fewer hardware companies, and I mean, the barriers to entry are obviously higher. One is capital, need for capital, but the reality is that it's really hard, and we haven't been able yet to get to the number of qubits that are needed. And so I think, again, over the past few months, several months, the industry has become maybe more honest with itself in that a few qubits are certainly interesting, and you know, before you can run, you need to be able to walk, and you know, we'll be able to discover amazing things with a few qubits. But in order to tackle useful problems from other industries that are not our own, we need thousands or more qubits. And so we don't have those, right? And one of the challenges has been scalability of some of the platforms that we currently have. And although, you know, supercomputing platforms and superconducting platforms and trapped ion platforms have done a lot of progress, there's been still a challenge in terms of scaling. And so photonic quantum computing comes a little bit to the rescue. I mean, the concept is not new, but more recently there's been a lot of progress. And so in that sense, I view it as a less mature technology. And so even if there's fewer qubits in photonic quantum computing platforms, my hope, my belief is that very rapidly we'll see more and more qubits, and these platforms will start scaling much faster. And so why are photons so exciting as a platform for quantum computing? Well, to start, they're very robust against noise, right? And so all of the noise and crosstalk effects that we see in other platforms really don't affect photons in the way they affect the others. So, you know, something that we really like, and that means, you know, one of the most immediate consequences is that these platforms don't need necessarily to be at very low temperatures. They can be at room temperatures. They're fast. You know, photons move at the speed of light, so they are fast. They have also arbitrary or one all-to-all connectivity as opposed to nearest neighbor connectivity. And although we haven't really taken advantage of that just yet because we don't have a photonic quantum computer per se, the hope is that this will open up computing power or resources. As I mentioned, no cryogenics, no vacuum systems needed. And finally, these are naturally, by the way they are defined, and I'll talk a little bit more about that, modular and extendable. So one of the key basic pillars of photonic quantum computing is what is called a large entangled state. So this is like the main computational resource that is used within those frameworks. And the way the goal then is to create this large entangled state. And so how do you create a large entangled state? Well, you have an array of qubits of photons, qubits that are getting entangled as they pass through the system, and then the system measures them, and then by measuring them, that's sort of as if you were applying gates in the more traditional quantum computing systems, and so those photons get confused, not confused, but consumed. And so it's a system where you constantly have an inflow of photons into this cluster state, and then the measurements just take these photons out of the system. Now, this, in theory, sounds all great, but there's several challenges to setting up a photonic quantum computing system, and that's why to date it's been we haven't seen that many at least commercial approaches until recently, which is very exciting. So one of the basic challenges that photonic quantum computing has faced in the past is the fact that the sources by default are probabilistic. So you'll get a photon sometimes, but sometimes you won't, right? And so it just becomes impossible to synchronize, or unless you find a way to do that. By default, your sources won't provide that. The same happens with entanglement operations. These are also probabilistic, and so sometimes they will happen and sometimes they won't. And then photon loss within the system. Certain materials are more lossy than others, and I'll talk a little bit more about that. So until recently, until we set up Orca, the only commercial approach to photonic quantum computing was silicon photonic quantum computing, and these are you might be familiar with SciQ and or Xanadu. These are two companies that have started earlier than Orca, and they've been using silicon, and they've done quite a lot of interesting progress lately. However, there's certain challenges, and I think everyone that's how companies were created, right? To get over these challenges. But to mention the ones that silicon photonic quantum computing platforms have, the most important ones. Well, one, they're developing chips, right? And so they're using foundries. The prototyping is an expensive process. It's costly to develop. Well, the material silicon is lossy by nature, and so photon loss is a real problem that needs to be overcome through other means. And then, because these are chips, right? Once they've been developed and you put all those resources to develop these pieces of technology, then every time you want to add more qubits or add something else or change something in the technology, it requires to go back to the drawing board and do that process again, right? So in that sense, it lacks, I guess maybe modularity is not so much the right word, but flexibility. And we in the current stage of quantum computing, where we're in a very, very early stage, and that's the fun part, we need that flexibility, right? We need to go back and make changes, and things change very rapidly. So this is a constraint of on-chip developments. Now, I want to briefly touch on Orca, and if you have questions on the science behind the quantum memory, and as I mentioned, our technical team, and we'll be more than happy to talk. But I just wanted to leave you with the basic principle behind it, which is basically just using quantum memories to synchronize photons and operations. And this is technically called temporal multiplexing. And it has several advantages, right? The first one is that it's very resource efficient, because basically you can, with one memory, you can synchronize several photons. You don't need to have what is called spatial multiplexing, where you have to put several photons through through the system and just pick up the ones that survive in a way, or that probabilistically show up on the other end. This is where I actually would like to transition towards the commercial side of things, because I think it's important to think about it. I think most of our community is focused on the technology and on the technical challenges, but at the end of the day, we need to build a computer that someone else will use and that will be able to sell. And so it is true that, you know, or it could be true that just the best technology will work, you know, the most stable, fastest. But I think if you break it down into pieces, it's very helpful to see why potentially certain platforms have quite a lot of advantages commercially, not only technically. So what's beautiful about, I believe, what Orca is doing is that there's a lot of, there's a big synergy between the technical advantages and the commercial advantages. So for one, the fact that, as I mentioned, the memory lets you synchronize operations and synchronize photons and basically just use less components. That instantly is a more resource efficient approach, which means, you know, less costly and also ultimately more scalable, because you don't need to use that many, you know, pack that many, a potentially impossible number of components within your system. Well, maybe I should have mentioned earlier, but the interesting thing that the memory that Orca built allows for is the use of optical fiber. So Orca is actually building the first quantum computer on optical fiber, and that's exciting because, well, optical fiber is, you know, most of the components are off-the-shelf components that have been around for years from the telecom industry, and so these are, you know, pretty much, I mean, give or take, for not for myself, but for you know, knowledgeable lab people, sort of plug and play, right? And so it's actually really exciting to work with a platform that, you know, very quickly, with not too much funding, we can put together a lab, and then maybe a second one, and then a third one, and actually start building these systems and putting them together and piecing and growing them as they go, which, you know, other technologies wouldn't allow for. And why is this important? I think commercially, well, it is important because it means that at this very early stage, when, you know, we don't have thousands of qubits, we can actually work with end users who are interested in understanding how toy models work and how maybe fewer qubits can actually provide insight on larger systems and so on. So there's a lot of interest in platforms that have these features. Well, I mean, photons, this is more from the photonic side of things, but the concept of distributed quantum computing, where you have several nodes, maybe running different calculations at, you know, across locations, and then they get together, communicate with each other. This is something that will need to be done through photonics, and so a platform that runs with photons is, provided that everything else works well, is actually the natural choice, right? And then related to this is the fact that we can't ignore the high performance computing industry, right? I mean, this is an industry that's been there for many, many years, understands the needs, the computational needs, has plenty of demand already. In fact, one could think of quantum computing as being there to solve many of the challenges that these platforms, that this industry has. And so ignoring HPC as a distribution channel is, I believe, in my opinion, a mistake that, I mean, maybe not so much now, but definitely early on, the quantum computing community, commercial community was doing. And so a photonic platform that interacts well with and can live in an environment that's already the environment that currently supports high performance computing is very attractive to those potential partners. And maybe on that point, it's worth also talking about the overlap between photonic quantum computing and just classical photonic computing. There's a lot of effort in photonic processors, photonic interconnects, all photonic platforms. And so this is a space that will, I mean, it's very fertile for quantum, but also from the classical sense. And then this is a bit of a, very simplified slide, and maybe just to leave you, I don't want to go too much into detail, but just looking at it in big strokes, what's exciting about photonics, both the silicon and optical fiber ORCA, right now the only commercial effort, is that we're already doing a lot of progress, but we're just at the very early stage of the technology. And so the maturity of the technology is slow, but actually, I mean, I labeled here as red, a warning. But in fact, I believe that's actually quite a strength, because it means that any sort of barriers that we're hitting now they just have so much room for growth, right? Whereas if you look at superconducting circuits, maybe just to pick on the old big whale, it's almost flipping on the other ends. It's hit several walls in terms of technology, and they've been able to overcome them almost bit by bit. But nevertheless, it becomes increasingly challenging to make progress in that respect. And so, I think photonics, we'll hear a lot of talk about photonics in the future. I think it's very exciting for anyone who's studied photonics or somehow has been exposed to it to enter the industry, and just the overlap, right? The overlap that it has with so many other maybe non-quantum areas, like non-computing areas like quantum communications, or non-quantum areas like photonic computing. It's just such a nice confluence of skills and just talent. And if you're in the field, or I love to hear more about maybe some of your backgrounds. Maybe I should have asked that earlier, but if you're a student, a physics student, thinking about where to focus on, what to study, all I can tell you is that there aren't enough good people in quantum photonics at the moment, and that I just see growth for the field. So anyway, I'll stop here. Maybe I should have said that I'd be very happy to go through questions along the way, but maybe it's easier if we do it right now.
Sure. Thank you so much, Cristina. That was fantastic. Are there any questions from anyone? Cristina, what do you think the time scale is? So you mentioned you don't think that photonic quantum computing is as mature as the other technologies. Do you think that will change in the near future? So there's huge amounts of money. For example, like PsiQuantum, I know they raised a round of over 200 million, I believe, and Orca and others. Do you think that will change in the near future?
Absolutely, yes. I do think it will change. We're already seeing, right? I mean, the progress that some of the companies, well, PsiQuantum is a special one because they don't share much, but I presume they're doing quite a lot of progress with that funding. Xanadu has also been pushing in their own way, and it's just a more yes, I believe it's going to accelerate. In terms of timeline, I think in the next 2-3 years we'll start seeing like the first very toy model systems, and then I think within 5 years we'll start seeing how I think scalability will be demonstrated, and from there, it's just a matter. It should be a matter of funding those platforms, and hopefully Orca is one of those.
Good, thank you. So there's a question about what exactly is Orca memory?
Without getting too much into detail, it's a rubidium vapor cell that basically gets excited with when a photon comes in and stores the photon, and then we have a method to release the photon. So basically, you can store on demand and release on demand photons. So yeah, it basically allows to synchronize at different points within your system. It's sort of this Joker card that you have.
Good. And there's a question now about photonic computing being in-house, like where someone buys a computer for themselves versus like a cloud computing model. Can you say anything about that?
Yeah, well, I think the future is in the cloud. Long-term future. I think that's what everyone understands. Now, it's in quantum computing. It's almost very easy to see the future, and so much harder to see the next, the steps that take you there, and how is it going to pan out. And so, yes, I think cloud is for sure where you want to go, and or remote access. But at this very early stage, what you have is also a lot of interest of on working with the development with the hardware, right? And just, I don't want to say tearing it apart, but having a little bit more of a say on how things go and playing with it. So although I think it'll be cloud, I think the first machines and systems we're going to see will probably be delivered so that there's more of a partnership than just a user provider relationship.
Okay, there's another question. How is photonic quantum computing used to simulate or accelerate problems in computational fluid dynamics? Does it guarantee solving the model without discretization?
No, I mean, at this moment in time, we're very far from, well, maybe Mark, you might be able to talk more about that. But I would say I don't think we have anything that's superior to the status quo, the classical status quo for computational fluid dynamics. There's hints, right? There's hints of tools that if we have enough qubits will be potentially better, but because we don't have those qubits, we don't yet. Mark, I don't know if you want to add anything.
Yeah, I don't think I have much to add on that. What do you see as key classical enabling technologies for photonic quantum computers, and which require advancements to make the computers feasible?
Oh, that's a great question. I mean, I'm being non-technical. I think I mentioned communications. and I think it's one of those areas that add a lot of value, and in fact, many of the skills are transferable, and many of the technology is transferable. And in fact, this is how the Orca memory got started in a way. I mean, the story goes that Ian Walmsley, Professor Ian Walmsley, when he was at Oxford, and Josh Nunn, they were looking in developing or looking at developing memories, quantum memories for quantum communication for a long time, but those memories need to have a long memory time or long enough for quantum communications. But they, at some point, they realized, working with the team on the computational side, on the processing side, that maybe it didn't have to be so long, right, to be able to synchronize operations within a quantum computer. And so I think, I mean, I can't name what are some of these classical enabling technologies that will be required to advance in the future, but what I can say is that these are where the breakthroughs come in, right? So I think keeping an eye on classical photonic quantum computing and quantum processors. I know Google has there's been a lot of work, particularly to solve neural networks in this space, and so I think reservoir computing processors is another space that in particularly focus on photonic that will see progress, and I think those will be able to translate into what we're doing in photonics.
Super. Does anyone have any further questions for Cristina? So thank you again so much for everything. I really appreciate it, and I know everyone else does as well.
All right, thank you. No, and as I said, very happy to talk to anyone who has an interest in this, and especially if it's a technical question, happy to send you over to the team at Orca, and yeah, I think keep an eye on photonics. There's a lot of promise, and I think it's going to accelerate very quickly.
Super. Thank you, everyone. Have a wonderful day, and I'll see you in almost 2 weeks.
Thank you, everyone.